the title's a bit of a mouthful, but it's just recommender systems. I picked a particular method and I applied it to content for people to consume on social networks. So it's just Rexis. Who here, just to kind of level set, so one of the challenges with the audience is that I want to make sure I keep everyone engaged and interested without going into too much detail. So who here's got an idea about recommender systems, maybe worked with them before? Cool. Who understands kind of deploying, production, machine learning stuff? Who's done it before? Cool. Right, so loads of questions at the end. I'm not going to be able to answer all of them because I got a lot of hands up, which is always positive. The talk is kind of a high-level grouping of all the things we learned along the way, and I'll just proceed ahead. Okay, so the first thing we wanted to cover off was the problem, so like what we were trying to solve. Then I want to spend a little bit of time about factorization machines as a method in comparison to other methods. We'll go into the mechanics of it in a small bit of detail, but nothing too much, so any PhD statisticians just hold your breath, because I'm not going to cover it. Then the third thing, and everyone in this room from the show of hands should get that, the data itself, preparing it for the machine learning algorithm was probably the hardest part. A lot of effort was spent there, and not in terms of cleansing, but actually the structure, because with the method that we used, the structure is probably the most important thing. As you've seen maybe in the past, your recommender is just a single line of code. It's the stuff at the top and the stuff at the bottom. It takes the most effort to get to. Then we talk a little about modeling and deployment. There's a really big lesson in that section, and I hope you all take it away. And then the fifth thing is just a single slide on further research. So places I'd like to go maybe in the future. So I finished this project up in June. I haven't really done anything with it since, but just to kind of cover off a few things. So the first thing is a business problem. So the whole idea is it's a social network with a number of different communities. So it's a professional network. So there could be a network for lawyers, a network for dentists, a network for electricians. Many members could be, so the lawyers could be members of the barrister and the lawyer community. And the whole idea was to be able to display content every time a user logs on to keep them engaged. So very, very similar to a Facebook feed. A post pops up, the user either likes it, shares it, or comments on it. Now, it's slightly different in that there's two types of content. There's user-generated content, which is individual users posting on their feed, and then there's API content from news providers. So my client had hooked up 2 or 3 news providers into the feeds, and they were popping up on people's feed when they logged in. So there was 2 types of content, and we wanted to make sure that they were getting the right mix of both native and external content, and then that they were also staying engaged. This is quite a complicated problem in that very little content actually gets engaged with, okay? But just because it doesn't get engaged with doesn't mean it's bad content. So the example, we'll go back to this a couple of times. Your Facebook feed, you'll see 10 things. You might click on 2 of them, like one of them. The other 7 things, they might not be bad. You just didn't really want to engage with them in that particular moment. So it's quite a tricky problem to solve. Just wanted to talk about the general structure. So content can be user generated or taken from a third party. Interesting content. So this is how we know that it's engaging. It'll be liked, there'll be commented on it, or it'll be shared. And content can be evergreen. So we talk a little bit about time-based stuff. The great thing about this problem is it's not really time-based, because good content is good content. So you'll see articles maybe from 2-3 years ago still coming up on people's feeds because people still like them, which is nice because you don't have to deal with dates and times, and you can kind of put that thing aside, which is important to remember. The tricky part to this one was that a user can be in many communities. So you can send them the same external content because you know they like it, but you can't send them the same internal content if they're in a different community. So if I post something in the solicitor community, I can't, my user group in the barrister community shouldn't be able to see it, even if the algorithm is telling me that, oh, this is really good content for this individual. However, that said, kind of behaviors are consistent across communities. So you do see users doing the same type of activities in the same volumes across all the different communities. So there's different user classifications, people who share a lot, people who comment a lot, people who like a lot. They all kind of generalize across the different communities. On the flip side though, the type of content each community consumes is slightly different. So there's a few bits and pieces in the air that you've got to be mindful of when you're tackling the problem. Now, that's the business problem. This is where the modeling problem comes to play. So this is kind of what we really want to talk about today, is what are we really trying to achieve? And all it is it's an optimization problem. So what we could do in a very simplistic way is just hook up whatever content is coming out of the users and the APIs and just put it in a feed, and as users log in, they see whatever comes to the front. But we want to be more intelligent than that. We want to model previous behavior and behavior of other users and generate the right type of content. So which method do we use to solve this problem? Do we use a collaborative filter? Do we use support vector machines? Like, what's the right one to do? And I kind of wanted to split. There was a couple of different problems we had to face, but the three big one was we needed a general recommender. So the whole idea of accuracy, while it's important, it's not explicit. So we don't need to be 100% right. It's not like someone's not going to die if they get the wrong Facebook or they get the wrong post in their feed. They're just going to go, nah, don't really like it, move on to the next one. But at the same time, you want to be hitting 2 or 3 posts out of 10 every time. So that's one thing to remember. Second thing to remember, speed and scalability, right? We've got many users generating a lot of content. We need to be able to pick up on trends in a relatively speedy manner and kind of feed those trends back into the user base. And then the third one, and this is something, if you haven't heard this or tackled this before, I would recommend investigating this concept a little bit more, because for me it was a really cool thing to tear into a little bit, in that you've got a sparse data set. So there's a lot of hidden behaviors. So there's a lot of behaviors that aren't present in the data, and it's really wide with low frequency. So you'll have a user that may like one piece of content every day or 2 days, and then a user that like one piece of content every month. So you've got this big matrix. I'll explain it in a little bit more detail as we get on, but just it's a real sparse data set, and some methods don't function very well with data sparsity, and that was the challenge we had to face. So these are 3 big challenges. We went and had a look at a couple of different methods to see which ones would answer our problem. We can go, like, there's 100 different ways to skin the cats here. There's 100 ways to approach it. These are these are based on research, not on results. So I read a lot of papers to make this decision. I didn't scientifically decide which one was best because I hadn't got that much time to go and run it on all different models. I'll challenge that. So we talk about a collaborative filter. You're all familiar with that for a recommendation system. It's used on Netflix. It's used, I think Amazon used it as well. You would have probably seen a few tutorials on Spark. The problem with collaborative filter was a little bit too accurate. So we were getting very narrow results, or we would get very narrow results. The same content would keep coming up again and again, which is not what we wanted. We wanted a variance of content every time a user logged in. They got something different, but it was also peppered with stuff that they like. Collaborative filter, it's good. It's suitable for speed. Collaborative filter also handles sparsity quite well. So that was probably the first go-to, but the real problem was it was generating almost too accurate a result. Then support vector machines, again, it's too accurate. It's fast, it works, but it just doesn't work with sparse data as well as factorization machines. So it's good with dense data where you've got a lot of interactions and a little sparsity. And then random forest, where I'm sure you may or may not heard of a cart, and something to do with trees. So there's a good general accuracy there. It's not very quick. Like that's debatable, but in this instance, it's comparative, and then it doesn't really work well with sparse data. So there's this method called factorization machines. There's a seminal paper in the end that was produced in 2010 by this guy called Rendell. He's come 2nd or 3rd in a number of different Kaggle competitions. So it's tried and tested. You'll see some more. They've extended it slightly. There's 4 or 5 libraries on it. It's quite easy to deploy. It's really good for general accuracy. It's fast, and it's fundamentally designed for sparsity. So it's designed for this big, wide data set with very little in it. Okay. So let's talk a little bit about factorization machines as a method. So please forgive me if I make any faux pas on this, but this is my interpretation of what I feel is important. Okay, so we all understand factorization, or sorry, how user interactions work. So I am a user. There will be a type of content, and then there will be many features to that content. So what are the keywords to that content? What is the age of the content? How many times has the content been liked? Did the user like it? Did the user comment? Did the user shared? And what you do with factorization machines is you split each interaction into a column, and then you make it either a binary, so it's a yes or a no, a 1 or a 0, and you can also include vectors in it as well. So what happens is, for every user interaction, you get an event, and the event contains all the possible permutations of all the other users, and it's just a 1 and a 0, 1 and a 0, 1 and a 0. So you start to get this really, really wide data set, which is complicated to handle for stuff like SVM. But the factorization machine is very it's able to understand and build on that set and give you an answer. So what happens is you get your 1s and your 0s, and then what it starts to do is it starts to put these into features. So it knows how to group them up, and then you get your target. So instead of having, you could have maybe 100 movies there, you could have another 100 movies there, and then different features about the movie itself, and factorization machines is able to group them into one big feature and compare them off each other. So there's a thing called pairwise comparison. So what it's trying to do is it's trying to compare the orange one with the green one, the orange one with the yellow one, and the orange one with the purple one, and then understand if they're dependent on each other. And then once it knows they're dependent on each other, then it moves on. And if they're not dependent on each other, it disposes of it and gives it a very low factor. So there's a lot more complexity to it than that. I don't want to go into it today, but I think that this is the way I interpret it, and we can talk about it a little bit later maybe. Okay, so this is the equation part. So your eyes might glaze over a little bit. So we have very simple stuff about there's a traditional bias. There's this concept of the pairwise interaction. So do the two factors interact? And then the factorization, so how strong are they, or how prevalent are they? And then there's a regression coefficient as well. So that's effectively that's how factorization machines works in a nutshell. Basically, you make a big wide data set, you put it through your model, and then it gives you predictability. It does have its limitations, though. So it's the fundamental of, because it's a general model, so it's easy to kind of throw stuff at. You get a general result, but if you've no domain knowledge and you don't understand your features, you're probably going to get pretty poor results because you're throwing too much at it. You're making it too wide, or you're over-engineering your features. It's not very good at dense data sets with binary outcomes. So if you're looking for a very simple yes, no on a single vector, it's probably not the best way to go. You're looking for a top 10 or a probability of engagement. That's where factorization machine starts to come in its own. It's a relatively newer method, so I think the first time I could research it probably was this paper in 2010 from Rendell. I'm sure it's been used previously in either ecology or some other more sciencey based stuff, but like there's a decent amount of stuff on Stack Overflow about it. There's a Spark library, there's an OR library, I think there's a Python library. So anytime you do something new, you should always try and be aware of how well supported it is and how much information you can get on it, because if you go down a rabbit hole, you want someone to have gone there before so they can help you along the way. I think that's really, really important. And then I keep saying it again, this is a general model, so predictions are general. I wouldn't use this for cancer diagnosis. I wouldn't use this for anything really serious. I'd use it for stuff where I need to get an indication of what may happen or what the behavior is. Okay, so that's a little bit about factorization machines. Talked a little bit about the business problem. Now I really want to talk about getting the data right. Now, forgive me if I lose anyone here, because this took a long time to conceptually get our heads around in the business, and I hope I can impart that to whatever degree to you guys today. So we need to kind of understand the structure of the data before we kind of proceed. And there's three distinct groups of information. There's information about the user, there's information about the content, and then there's information about the context that content has in relation to the user. So a user is X, members of community Y, logged in then, total amount of comments, total amount of shares, that's a user feature. Content would very much be focused on keywords, source of the content, and then context. And this is a real strong predictor, is was it liked, was it shared, was it commented on, okay? So they're the 3 buckets of features that we broke it down into. And sorry, I'll just go back on these a second. So once you understand that, then you can go in and write loads and loads of SQL into the database. So I'll do the architecture at the end, but there was a lot of queries written to try and build that big flat wide matrix, and it wasn't easy. So I just want to talk about user behavior a little bit, and one of the advantages or disadvantages. So we began from the very get-go, we did a quick scan of our data, and we found very clearly that a user who's an admin or a moderator, that's really, really important you call out, and it was impacting our predictions quite a bit, so we ended up just cutting. I think there was maybe content, or they generate too much content, or they don't doesn't really work for recommendations. And then there's also, on the other side of it, there's a whole load of dead users. So users which never logged in, nor will they ever log in. So they've got an account set up once, they may have logged in once, they may have not even logged in at all. Got to get rid of them. So for the purposes of feature manufacture, unimportant stuff was like user behavior, engagement, and then count of community membership. So we found that like users logging into many communities didn't really matter. The behavior of the user, so how many likes, take that into account, and then engagement, so how often, frequency, that kind of time-based stuff doesn't really matter that much. The factorization machine will take care of that. And then we start talking about how we structured the content, and you just basically I spent some time trying to explain this today or this morning, and I think really it's just about, you need to take your content and you need to give a context, and that was the way we approached that. So in the event, did the user like the content? In the event, did the user comment on the content? In the event, did the user share in the content? And then for the content itself, we just did some keyword lookups. Sorry, we did some keyword extraction. So we just did a basic get rid of all the stop words in every piece of content, decided which keywords were in it, and added those keywords into our matrix. So we get like this big, wide data frame with each keyword in there. And it worked reasonably well. So there's a really simplistic approach of how to shape up the data frame. But like any time you tackle social behavior or user data, you're always going to get this hockey stick where there's 80% of the behaviors are generated by 20% of the audience. And if you see anything, if you see behavior that's not like this, I'd suggest go back and check your data. It sounds weird, but if you see a nice flat, everyone's engaging at the same time, at the same level, then you've probably done something wrong, or you're looking at too narrow a cohort. But I just put this in because it's a ready reckon for me all the time. If I see the hockey stick, I know I'm on the right track. If I don't, then I probably need to go back and do some more work. So, as I said at the start, the final result was this really massively wide data frame with every interaction the user had with the system was an event, and each event had either a 1 and a 0 on many different columns. Okay, so user, content, and then all the features pertaining to that content. And then we just threw that into the model and it worked, right? No, not really. So so we've got the data now, it's all shaped up, looking pretty good. As I said, there was a lot of SQL behind that. They used the MySQL server, so we were rummaging around. They had 2 databases. They had one for the guest events, and then they had another one for the content events, and we had to try and put the 2 of them together. So now we talk about modeling and deployment. I think I want everyone to kind of pay attention to the steps, not the technology with this. I think there's one key learning which I'm going to give you shortly. So unfortunately I was away yesterday, so I didn't make yesterday's conference, but the big thing, or the big trend or challenge that you face as a data scientist these days, it's not making a model, it's actually deploying it into production. How do I get my Python script into a production that it can be called by an API, by a service? The client was very explicit in that they wanted to surface the content using their they had an existing stack that would publish a stream to a user when it logged in. They just wanted our API to be able to call, they want to be able to call our API. Our API would respond with a content ID, and then that content ID would then be fed into their stream. So we use this thing called, it was called Dato, now it's called, then it's called Turi, and it got bought by Apple in August, and it's only open source from now on. So you can only get it with an academic license. So the lesson there is be wary of what you use, because it mightn't last forever, okay? There's a really cool alternative called Domino Data Lab. I would recommend everyone have a look at. What Turi do is they allow you to take a lot of data, build a model, and then deploy that model as a RESTful service, and then you can call the model with an API. So we'd send the model a guest ID, and the model would then respond with 10 or 20 different content IDs, and those content IDs would then go into the user stream, and then the user stream the user service would then query the content store, and then the content store would respond and output the data. So that's it. I think it was $10,000 a year per seat, so it wasn't cheap, but we got to use it for. It originally came from an open source tool called GraphLab, and you can still use GraphLab, but just as I said, be really aware of what anything with Spark in a similar vein before, but is it there? Now, the one cool thing, aside from Turi having a very developed factorization machine library, is that they had these things called Sframes, which are pretty similar to an RDD in Spark. So the whole idea is it's a scalable out-of-core data frame. So if anyone's ever brought like 1 million lines or 10 billion lines into your laptop and just watched it fall over, yeah, that's not great. So these S-frames are out-of-core data frames. So you can actually use them on data sets which are bigger than the amount of RAM you have available. So I just call that out as that was really the two killer features. That the reason we picked Data was it had the API RESTful service deployed on AWS like really, really quickly, and it had these S-frames because we knew that we were going to get a really, really wide memory intensive data set, and we needed to solve that problem. And I think Spark, they had the RDD behaviors. The user arrives, and we gather those behaviors and we gather the content. If I was to give you one piece of information about the slide, just be aware of the size of your data frame and try and build something that will tackle that problem in a reasonable manner. And I think Pandas is in memory, but someone else. So let's talk a little bit about the architecture. Which is all of their content, so all the posts that all the user made, all the content that the external providers have generated, each had a content ID and had a lot of features. Then we have the guest data, where the guest is from, and what communities they're a member of, all those different behaviors. The user arrives, and we gather those behaviors and we gather the content. Then that goes into a factorization machine model, and then each piece of content is scored and each user is scored, and then we use those scores to cycle it. We want to get new scores, we want to update it, and it's got to be real time because that's the way Facebook works, right? So one of the big challenges, or one of the kind of the issues or the back and forth we had with the client on that was this concept of batch versus online. I am sure if anyone's trying to build a service every hour, every day, every 4 hours, every 6 hours, or do I make it really, really fast and it works in real time? And what we found and what I found outside of this project is generally the clients are always like, oh, we want to run it real time. We want to run the model each time someone logs on. We want to recycle it. We want to get new scores. We want to update it. And it's got to be real time because that's the way Facebook works, right? And that's really not viable. And you should never try and aspire to that, because 9 times out of 10, an hourly update will do, right? And like if we're talking algorithmic trading, yeah, maybe, 5-minute updates, but you should be able to get the same results in an hour, every hour, than you would every 5 minutes. So the battle we had with this client was that they were like, oh, we want trending articles. We want to get trending articles up to make sure that if a story is breaking, that it arrives in real time. So we said, okay, that's cool. Let's have a look at it. And what we ended up doing, the compromise came when we started talking about cost. So we were like, well, we can do trending. That's no problem at all. But AWS are going to start charging you a lot of money for the servers that you need to do this. But if you run it every hour, you'll get pretty much the same result. And you know what? It's going to be way cheaper and way better. And they were like, oh, that much cheaper? Okay, that's great. So you kind of step away from that. And it's something that it's a discussion I think it's worth having. So where we were really fast was we had that scoring engine optimized. So the scoring bit, they were able to call that really, really fast and get the 10 articles back as quick as they could. And then, but the factorization was much more slower, much bigger. But with the Sframe, I mean, when I say we had about 100,000, we had 56,000 guests, and I think we had maybe 5 million events, which to anyone who's done kind of event-driven stuff before, that's not massive, like that's not big. So the problem we face is we could have ran the online job at the start, but we knew that it wasn't scalable. So we didn't want them to come back in a year, 3-4 months later and be like, hey, why are we getting charged so much money for this? So just want to talk a little bit about the architecture again. Data is run off C#. So it was built originally in C# and it's wrapped up in Python and OR. And we hosted that Azure shouldn't be there, it's AWS. They wanted originally to use Microsoft Azure, and then we talked to their engineers, and their engineers used AWS for everything else. So naturally we went for that. Okay, and I think I'm coming to the end of my talk. What I just want to talk about is further analysis and further places I think I would have liked to bring this. The first thing is, so we talk about seeding content and trying to understand if we inject arbitrary content into the system, how will that affect the recommendations? So if we just say, well, we really want to either advertise or we really want to do something different, or let's say post an announcement, how will this skew and affect the model? The second piece was we'd actually know consumption tracking. So we'd know a way to know the success of a piece of content. All we could do was have this inferred behaviors. So it would have been great to be able to A/B test stuff and say, well, the holdback on this piece of content was 5%, and you know what, the click-through rate was X and the lift was Y. Yeah, brilliant. We now know our model's been tuned. I mean, we did some stuff for root mean square error, but we didn't really, because it's a generalized model, it didn't really come off as well as we thought. And then the third thing, which is something related to A/B testing, if anyone's looking at content consumption and A/B testing, there's this idea of presentation bias, and it's something that is kind of interesting. So based on the rank of the content, how likely was it to be consumed? So if it's always first, will it always be consumed? Sometimes content needs to be third or fourth down the rank to get there. And that's pretty much it for me. I try to keep it as short and sweet as I possibly could. And I'm happy to take questions now if anyone has any.
When I look at this sort of technology, it's obvious what it's doing in Facebook or similar. Whether that's something sort of very technical and it's a social group, something related to Stack Overflow, or whether it's, sort of pure public consumption. Do you think this kind of analysis is going to extend into other sorts of web consumption? Is this stuff going to spread out of the social media realm into, professional tech recommendations? Is this going to...
So we're talking about recommendation systems, and I think there's a lot to be said, to be really concise, there's a lot to be said for a rule-based model, right? this stuff is great when it's generalized and it's wide, but when you start talking about very narrow instances, job recommendations, stuff like that, I'm not sure it's of that much value outside of a rule-based or a good cart or whatever. I'm trying to think of other use cases, but really for me, this is only suitable when you're trying to encourage human behavior rather than drive a click-through. I think there's a really good Kaggle competition on factorization machines for ad roll, where they went for a click-through on ads. I think that's a good example, but when we talk about recommendations per se, it's fundamentally down to how important the recommendation is. Does that? I'm not sure I really answered your question, but kind of. I have no vision, but that's what I think. Yeah. Cool. The gentleman there with the glasses. Yeah.
Sorry, just wait.
Oh, sorry.
Thanks.
Yeah.
On one of your slides, you mentioned that from what I figured is all the users were logged in, so all the users were. It was known this is the user.
It's a wall garden, yeah.
Yeah. So sorry, I was late for the.
No problem.
How would calculating like anonymous users and connecting them to this is one user based on different access. So is that feasible, and how would that affect the performance of your system? So what I'm saying, there's you create a profile of the user.
Yeah.
And then based on no known like a unique ID, you connect. Oh, okay, this is the user.
Okay, so I think there's maybe two things that we're talking about there, and one of them is the idea of anonymous users and unknown users versus known users. So how does Google generate an ad for you when you have incognito mode on versus how does Google generate an ad for you when you're logged in and they know who you are? And then the second thing is, how do you group user behaviors together based on unknown users? So in this example, the way it's solved is that the user is unknown. They log in for the first or the second time. However, there is a history of events of unknown users who have logged in for the first or second time in this community. Here's their behaviors. Here's the content that they liked. So it's not so much about it's not the problem of identifying the user. It's the problem of building a profile of an unknown user in the model, and that's factorization machines takes care of that very well. When you talk about the difference between known and unknown, it's a whole other ball game, and it's because if you look at anyone's web behavior, 80% of it is unknown. If you look at any of the public sites, or if you go to Google Analytics, like 80% of the guys are first-time users. They've never been seen before, and that long tail is actually quite. You don't get that many features with those users, so it's difficult to relate to them. Did I answer your question, or kind of? We can talk about it afterwards. Cool. Is there any more?
Any more questions?
Hi. Maybe you mentioned this already, but I'm interested in the width of the frames. So when you actually want to add the new keyword, for example, new column in this frame, when do you update your model? Every hour?
Yeah. So we batch it every hour, and we'll add a new column to the frame.
Okay. How long will it takes to actually update the model?
5 minutes, 5 or 6 minutes. Like it's
it's pretty fast. Yeah.
It's really fast. Like the S-frame is phenomenally fast, and like it just works. Like I think the thing that we probably, and in that time, it was all about the keyword extraction from the new content. So if you had a big chunky article, like it would take a bit of time, but the generation of the extra column is pretty quick. They're designed, the S-frame is designed. That's why Apple spent 200 million on them. The S-frame thing it's a cool piece of kit.
Cool.
Yeah.
And the next question is, you mentioned the action the user took actually, it's a comment or like or
yeah.
You also store this data as a part one of the columns, right?
Yeah, it's a binary, so it's a 1 or a 0. So
okay, and how the factorization machines decide whether it's like a description of content, or it's an action, or it's a user?
So
is it built inside the factorization machine algorithm?
So what factorization machines does is it tries to understand the latent space. So it tries to understand what's implied in that like, not the explicit act of the like. So to your point, the factorization machine does that for you.
Okay.
Is that, yeah? So you don't have to weight the like. You don't have to decide, oh well, it's a 0.5 of a like because it's from X, Y, or Z community. It's just a 1, and then factorization machine looks at all the other activities across that particular event, and then looks laterally as well, and then says, yep. That's an indication of whatever. Does that make sense? Or
Yeah.
kind of, it's like statistics. You never really understand it. You just get used to it. Is what I got told. So,
Sorry, any more questions?
not him.
Thanks for a great talk.
Thank you.
For the factor matrix
FM.
FM.
Yeah.
For the FM, what's the loss function that it optimizes on?
I don't know.
Oh, okay.
So it does, from what I can gather, it does a lot of gradient descent is how it works, how it decides where it's going to get to. But again, it was black box for me. I didn't want to spend too much time figuring that out. Well, I can send you, if you want to look at the Rendell paper, it'll talk a lot about it. And then if you want to look at there's a really exceptional talk on SlideShare by Rendell and another guy from Google, where he compares all the different recommendation methods. It's like a 72 slide deck, and he'll talk in detail about that. Apologies if I can't answer your question.
That's perfect, thanks.
Super.
And I don't know, maybe a follow-up question on that. You had a slide there where you said collaborative filtering was too accurate versus general accuracy.
Yeah.
What do you mean by that? Or
So too accurate? Yeah, it's a good question, and I guess I've tried to answer it in my head as best I can. And really, the collaborative filter, the use case is you constantly show the same things again and again and again to get the right response. So you always show the Netflix example, you'll constantly show these 5 action movies because you want to get the click-through on the 5 action movies. But factorization machines shows you 10, and then it shows you another 10, and then it shows you another 10, based on the latent behavior of all the other people around you and all the other space. There's a little bit more meatiness in this idea of pairwise actions. And I don't think collaborative filters doesn't take into account the pairwise actions. It kind of tries to group it all in one big function, and that's the distinct difference. But I try to explain it succinctly. Maybe we should catch up afterwards. Super, great.
Any more questions?
Yeah.
Thanks, great talk, Conor. Just quickly,
Yeah.
so the matrix that you showed to train the model, that was really wide,
Yeah.
and you said it was very wide.
Yeah.
So I'm imagining millions of columns wide.
Yeah.
Does that continue to grow as more content is added to the network? And
So-
or is there an algorithm that kind of removes old content as you go?
You're always, no, it continues to grow, but the rate of growth will obviously slow down because you can't. There's only so many keywords. There's only so many interactions. So you expect your interactions to kind of top out on your first load. Where you're really going to run into problems is the keyword extraction, and I think like when the performance starts to degrade, you can start doing some TF-DIF and just kill some stuff that isn't gonna work very well. But so I collaborated with. I actually didn't. There was a PhD from the US who I worked on with this, and me and him. I didn't believe it was going to be as quick as it was when we started off. I kept saying, no, it's big wide thing's not going to work. And it's counterintuitive, but it actually does work to have this massive, big, sparse data set, and just the S-frame and the method really, really soak it up quite well. Oh, gentleman with the glasses, you're asking an easy one now. You've been giving me like... Yeah. So how do you do... So the frame itself, so how do you distinguish a recommendation between the user and the community? So what you're trying to do is you will score each piece of content in relation to the user. So there's a probability score against that content for that user. So it's quite chunky, but with the Dado service you can query it quite quickly. Does that answer your question? Cool.